Welcome to Lesson 20, EMF, Internal Resistance and Potential Dividers. Here's the plan for today. The EMF, or electromotive force, given by the symbol epsilon, is the energy per unit charge that the cell produces, measured in volts, just like a potential difference. That's the full amount of energy the cell gives to each coulomb. But the cell is made of real material, and charge has to fight its way through the cell itself. That opposition is the internal resistance, little r, and we draw it as a little box sitting alongside the cell. From now on, big R means the resistance outside the cell, in the external circuit, and little r is the resistance within. Now, the energy has to go somewhere, so the EMF splits. Some is delivered to the external circuit, I capital R, and some is wasted inside the cell itself, I little r. That gives epsilon equals IR plus IR. Rearranging gives the terminal potential difference. What you actually measure across the cell's terminals. V equals epsilon minus I little r. And that's the punchline. You never get the full EMF out. The bigger the current you draw, the more you lose inside, and the more the terminal voltage sags. That's why your car headlights dim when you turn your engine over. You're drawing a huge current, so I little r is big, and the terminal voltage drops. Two results that you need to remember. First, the power delivered to the external circuit is at its maximum when the external resistance exactly equals the internal resistance, when big R equals little r. That's worth remembering as a stated fact. Second, how do we actually measure epsilon and little r? Take our equation, V equals epsilon minus I little r, and compare it to Y equals mx plus c. If you plot the potential difference V on the y-axis against the current I on the x-axis, you get a straight line whose y-intercept is the EMF, and whose gradient is minus the internal resistance. That's a classic required practical graph. Make sure you know how to interpret it. These calculations often look intimidating, but they always follow the same 4 steps. 1. Draw the circuit, always. It makes it so much easier to understand what's happening. 2. Find the current, using epsilon divided by the total resistance of everything, and that total must include the internal resistance. Look at the system as a whole. 3. Once you have the current, you can get the potential difference across any series resistor from V equals IR. And 4. For anything in parallel, find the potential difference across that parallel section, then divide by the individual resistance to get the current down that branch. Draw it, total resistance, current, then work outwards. Follow those 4 steps and even the nastiest circuit falls apart. Some quick rules for combining cells. In series, the EMFs add together, and if one cell is connected the wrong way round, you subtract its EMF instead. But the internal resistances always add, no matter which way the cells face. Always. For identical cells in parallel, the EMF stays the same as a single cell. You don't get more voltage. What you gain is that the internal resistance divides, so you can draw more current without the terminal voltage sagging. That's why parallel cells give you a beefier supply rather than a bigger voltage. Finally, the potential divider. What does dividing potential actually mean? It means supplying a variable fraction of your source voltage, taking a 12-volt supply and tapping off, say, 4 volts from it. It works because 2 resistors in series share the same supply voltage in proportion to their resistances. So the output taken across R2 is the input times R2 over R1 plus R2. If the 2 resistors are equal, you get exactly half. If R2 is 3/4 of the total, you get 3/4 of the voltage. Now, with fixed resistors, that's a bit inflexible. You'd need to physically swap components to change the output. So instead, we use a sliding contact, a potentiometer, which lets you slide smoothly between 0 and the full supply voltage. That's like your volume control. And here's where it gets clever. Swap one of the resistors for a thermistor, and the output voltage now changes automatically with temperature. Swap it for a light-dependent resistor, and it changes with light level. That's the basis of every sensor circuit: a temperature alarm, an automatic street light. The potential divider turns a change in resistance into a change in voltage that a circuit can act on. That's the end of the video, and the end of electricity. Next time we go back to some more advanced mechanics. Thanks for watching. Check out my tutoring page below.